right, so here are the notes for section 10.2, which is a Taylor series. So what a Taylor or a Maclaurin series does is it's a polynomial that approximates the shape of any other given function. So it follows this pattern. So this is for x equals 0, which is specifically a Maclaurin series. So it's f of 0 plus f prime of 0 times x, so on and so forth. So you count up the x's, so derivative 0, second derivative over 2 factorial. So you have your derivative over the corresponding factorial, so on and so forth, until you get however many terms you need. So fourth order would mean we're going to end at x to the, whoops, sorry, I can't see it. So the fourth order means we're going to end at x to the fourth. So if we look at this, so example 1, how this works, find the fourth order Taylor polynomial that approximates y equals cosine 2x near x equals 0. So what we need to do, let's see here, is, so I need f of 0, I need f prime of 0, I need f double prime of 0, so that's going to be my x squared term. Third derivative of 0, that's my x cubed, and then the fourth derivative at 0. These are going to be the values here that are going to be my coefficients, or part of them. So let's see here. So f of 0 is just plug 0 into your original equation, so the cosine of 0 is 1. So this gives me 1. So f prime of 0 would mean I take the derivative of this and then plug in 1. So f prime, the derivative cosine of 2x is negative 2 sine 2x. So if I plug that in, negative 2 sine of 0, I get 0. Okay, so f double prime, so I need the equation for the second derivative, so that's going to be negative 4 cosine 2x, which is going to come out to be negative 4. Third derivative is going to be positive 8 sine 2x, which is also 0. And then the fourth derivative is going to be 16 cosine 2x, which comes out to be 16. Then I'm going to go up to my pattern here. So it's f of 0, so it's going to be 1 plus f prime of 0, so 0 times x. That's this, whoop, can't see it. Kind of off the screen. So f prime of 0 times x plus the value of the second derivative, negative 4 over 2 factorial x squared plus 0 over 3 factorial x cubed plus 16 over 4 factorial x to the fourth. So this is going to be 1, that term goes away. Negative 4 divided by 2 factorial is 2, so negative 4 divided by 2 is negative 2. That's 0 again. This 16 over 4 factorial, so 4 factorial is 24, so 16 over 24 reduces to 2/3, so plus 2/3 x to the fourth. Now what happens is, let's look at the graphs here, menu graph. So cosine of 2x, and we'll type this 1 minus 2x squared plus 2/3 x to the fourth. Draw. So there's, if you look, the blue one is the actual cosine function. The red one is my approximation. If you look close to x equals 0, so close to the center of the graph, the two lines match up pretty well. The more terms this thing gets, the more closely the red curve will match, or the farther out it'll match. But close to 0, it's almost a perfect match. It doesn't start to break up until you get farther out away from here. So that's what it means by having a polynomial approximate an actual function. So the graph of this is very close to the graph of this at a close to x equals 0. Doop-a-doo. All right. So you can also generate a series centered at any location. That's a Taylor series. So it's almost exactly identical. Instead of having just x's, I have x minus a's where I'm centering it. So find the Taylor series generated by f of x equals e to the x at x equals 2. So let's see here. You want just the generic one, or we want the full-on thing? So let's see here. So f of 2, because it's f of a, is going to be e squared. Now the thing is, next one would be f prime of 2. Well, f prime is also equal to e to the x, so also e squared. The second derivative at 2, well, the second derivative is e to the x, so also e squared. And this is going to go on forever. It doesn't matter what it is. So what my formula actually is, I can just write generic, or something generic. It's the sum starting at 0, going to infinity. So the top is always going to be e squared. The bottom is always the factorial, 0 factorial, 1 factorial, 2 factorial, times x minus 2 to the kth power. 0 first, second, third, so on and so forth. So this is a Taylor series generated by e to the x at x squared. The more terms I have, the closer it matches. Okay. Find the third order Taylor polynomial for this equation at x equals 0, at x equals 1. Okay. So over here, so f of 0 is going to be, plug 0 into this equation, I get -5. F prime of 0, so I need the derivative. So the derivative is going to be 6x squared minus 6x plus 4. So this gives me 4. The second derivative, so that's going to be 12x minus 6, is going to be -6. And the third derivative is going to be 12. So 12. So my pattern is f of 0 plus f prime x plus f double prime over 2 factorial x squared plus the third derivative over 3 factorial x cubed. So this is -5 plus 4x minus 3x squared, 3 factorial is 6, plus 2x cubed. If you notice, this is actually the exact same thing, just written in the other order. So over here, f of 1 is going to be 2 minus 3 plus 4 minus 5. So this is -2. This first derivative of 1, well, I already have my first derivative equations over here. So if I plug 1 into this equation, I get 6 minus 6 plus 4, which is 4. Second derivative at 1, so that's this. It's going to be 12 minus 6, or 6. And the third derivative at 1 is just going to be 12 again. So it's going to be f of a plus f prime of a times x minus a plus f double prime over 2 factorial x minus a squared plus f triple prime over 3 factorial x minus a cubed. So let's see if we can clean this up. So that's -2 plus 4 times x minus 1. That's 3 x minus 1 squared. That's going to be 2. So there you go. There's your Taylor polynomial. Typically, you flip the orders on both of these because you want them in descending order. So this one would actually originally be 2x cubed minus 3x squared plus 4x minus 5, which is exactly what we had before. This one would be 2x minus 1 cubed plus 3x minus 1 squared plus 4x minus 1 minus 2. If you actually wrote it in the correct order. Now this actually is the exact same equation as this if you FOIL it out, because the reason this happens is that you're looking for a third order Taylor polynomial for a third order polynomial. So these equations, actually doesn't matter where you center it, are always going to be the same. So I could center x equals 2, and if I worked out all my expansions, I would still end up back here because this is a third order polynomial. So to approximate a third order polynomial, you don't need to, you already have it. Okay, so combining tables, or sorry, Taylor series, find a Maclaurin series to represent this function. What is this interval of convergence? So let's see here. So we need to do some approximations. So e to the x, Taylor polynomial for e to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus blah, 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 all the way up to x to the nth over n factorial. So if we wanted to do e to the 2x, that's just going to replace all of our x's with 2x's. So 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus blah, 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 up to 2x to the nth over n factorial. So then if we want to do e to the 2x minus 1, we just subtract 1 from this, which just eliminates that term. So we get 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus blah, 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 all the way up to 2x to the nth over n factorial. And then if we want to do this, e to the 2x minus 1 all over 3, we just divide all these guys by 3. So 2/3 x plus 2x squared over 3 times 2 factorial plus 2x cubed over 3 times 3 factorial plus blah, 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 2x to the nth over 3 times n factorial. And that is your Maclaurin series without having to generate or do all the derivatives. You can base it off of something you know and just perform the operations. So here's just a general table of Maclaurin series. So if you want to approximate 1 over 1 minus x, that's this, 1 plus x squared, blah, blah, blah. 1 over 1 plus x just has alternating signs. E to the x, here's the shortcut I used up above. The sine of x and the cosine of x, they're approximations. If you notice, the sine of x has only odd powers of x, the cosine of x has only even powers of x. The natural log of 1 plus x goes to this guy. The inverse tangent of x does this. So there's our summary table for Maclaurin series. And that brings us to the end of this section.